evening, everyone. My name is Andrew Fracknoy. I'm the Emeritus Chair of Astronomy here at Foothill College, and it's a pleasure for me to welcome everyone here in the Smithwick Theater and everyone viewing us on the web to this lecture in the 20th Annual Silicon Valley Astronomy Lecture Series at Foothill College. These programs are co-sponsored by 4 organizations: the Foothill College Physical Science, Math, and Engineering Division, the Astronomical Society of the Pacific, the SETI Institute, and the University of California Observatories, which includes the venerable Lick Observatory on Mount Hamilton in San Jose. And we're delighted to have their help in publicizing and sponsoring these outreach events. Tonight's speaker is Dr. Phil Marshall. Dr. Marshall is a senior staff scientist at Stanford's SLAC National Accelerator Laboratory. His research interests are in observational cosmology using gravitational lensing. What he does is to weigh galaxies and measure the expansion rate of the universe. Not bad as a job description. He is a member of several collaborations developing new methods to take advantage of the enormous flow of data that will be coming back from the Rubin Observatory's legacy survey of space and time. He received his PhD from the University of Cambridge, where he first got interested in techniques for measuring astronomical objects that we may not be able to observe directly. And he is currently the Deputy Director of Operations for the Vera C. Rubin Observatory. And that indeed is his topic for tonight, an upcoming project which everyone in the astronomical community is looking forward to. The biggest sky survey ever taken, exploring the universe with the Rubin Observatory. Ladies and gentlemen, please help me welcome Dr. Phil Marshall.
Thank you for all being here. It's nice we get to spend the evening together. Okay, so as Andrew said, I'm here from the Rubin Observatory and SLAC National Lab, and I wanted to tell you a little bit about where we are with this exciting new project. It's been under construction for a while now, but we're getting very close to its operations period, where we turn the telescope on and start observing the sky. I also wanted to show you a little bit about the research we've been doing at SLAC to use the data coming from the Rubin Observatory. And along the way, I thought it would be good to try and understand a little bit what it is to be an explorer. What does it mean to be exploring the universe in the 21st century? So you might ask, well, where did I get this idea from to base the talk on this theme? So I got the idea for this talk, Exploring the Universe, from talking to my wife, actually. She asked me when we were dating, what is it that you do? Why do you do it? And I spent some time trying to explain it to her, and she said, oh, you're like Magellan. And I thought, well, am I really like Magellan? I'm not sure. But then I did some searching around, found this interesting quote from Edwin Hubble, astronomer in the early 20th century. And he wrote, or said, equipped with his 5 senses, man explores the universe around him and calls the adventure science. So I think it's not unfair to think of scientists as explorers, but let's get into this a little bit more. Where do we start with doing cosmology with observatories like Rubin? We start with some good questions. So the questions I'm interested in, perhaps you're interested in them too, include where did we come from? How does the universe work? And what else is out there? And these aren't very different from questions that explorers have been asking since the beginning of history. So here's a famous explorer. Here is Magellan. He started with a different question. His specific question, I think, was something like, is there a way to reach the Philippines by sailing west? But that was a specific kind of question that he would have written in his proposal. I think really he was just interested in what was out there. So what do explorers do? Well, they propose. He had to propose to get funding to go on this voyage of discovery. He did a lot of preparations, and then he set out. Here's one of the ships from his flotilla. This is the Victoria. This is a special one. He left in 1519 in 5 ships with 273 crew on a very famous voyage, the first one around the world. Only 18 of them returned 3 years later on this one ship. So I'm hoping that one way in which I'm not like Magellan is that at the end of the LSST survey, we'll all still be alive. Okay, so what did Magellan and his crew discover? Well, what they did was set out to find a way to get to the Philippines by sailing west, and they found it. So here on this map, in the red circle down here, this is the Straits of Magellan. This is what allows you to sail safely around South America and emerge in the Pacific, which has never been done before. So we can think of this map as it's the main result of Magellan's mission, made by Diogo Ribeiro, and it showed everybody in the world a new path forward. And when you get through the Straits of Magellan, you get to the Pacific, there's this whole ocean of possibility out there that people didn't realize was there. It's interesting to ask, well, what was Magellan's motivation? Here's the man in his own words. The sea is dangerous and its storms terrible, but these obstacles have never been sufficient reason to remain ashore. Unlike the mediocre, intrepid spirits seek victory over those things that seem impossible. He's a product of his age, Ferdinand Magellan, back when being macho was still cool. He goes on, it is with an iron will that they embark on the most daring of all endeavors, to meet the shadowy future without fear and conquer the unknown. I think that was really what was driving Magellan. He wanted to see what was out there. Okay, so what does exploring look like in the 21st century? There are places on the Earth that we haven't been to, mainly the depths of the oceans, or the very deepest parts. You hear talk of manned missions to Mars, getting further out into the solar system. But there are other ways that we can explore the universe, as you know, staying here on the Earth. And here's some good words to set us off with. This is from Marcel Proust. The real voyage of discovery consists not in seeking new landscapes, but in having new eyes. So I'm here to tell you about a new pair of eyes we're getting. This is the Rubin Observatory. We should think of it as the biggest digital camera in the world, mounted on an 8-meter class telescope that will feed a data facility that will automatically process all the images coming out of this big telescope, the world's biggest camera. And that data set, 500 petabytes, will be crunched in order to make measurements that astronomers all over the world can use. 500 petabytes, by the way, is an unimaginably large amount of data. It's enough to store a copy of every book ever written in every language currently in use. Okay, so where are we with the Rubin Observatory? Here's the summit facility on Cerro Pachon. It's a mountain in Chile. Here's where we are so far. You can see the back of the building where we'll do maintenance of the telescope and the camera and so on. You can see the dome. That's that open structure that's gradually being closed in. This is a recent photo of the panels on the dome going up. So it's a big facility. Here's a slice through. Interesting things to point out inside the observatory are here. You can see down here, this is the control room. This is where the observing specialists will operate the telescope during the night. Here's the clean room in the back where we'll maintain the camera. I'll tell you a bit more about in a minute. We have our own mirror cleaning facility here. And in fact, that's already in action, preparing the main mirror, whose name is M1, M3. I'll explain why in a second. Other things to notice, the telescope in its dome up here on the left. And here's a great big elevator for moving the mirror up and down when we take it off to clean it and put it back on again. So the telescope that's sitting in the dome that will be taking the images is called the Simony Survey Telescope. It weighs 300 tons, but can slew 90 degrees in 9 seconds. So just to give you, I like to act this out. So 90 degrees in 9 seconds looks like this. 1, 2, 3, 4, 5, 6, 7, 8, 9. So for a 300-ton telescope, it's pretty fast. Why does it need to go that fast? Well, it's because we have a lot of sky to cover, and we want to keep imaging it. That's what the Simony telescope does. It repeatedly images the sky. It will take a deep image 20 gigabytes worth of data every 40 seconds on average, and we'll do that for 10 years. So inside the telescope, if we take away all the mounts and the hexapods and all of that stuff, and just leave you with the optical elements, the mirrors, you can see here that there are 2 mirrors that are actually 3 mirrors. This big one down here is the primary on the outside, the outer annulus, and then in the middle part is the tertiary, and mounted above it, there's a secondary mirror. Okay, what does this mean? Maybe better to show you a picture over here of what the light is doing as it comes into the Simone telescope. So imagine a star, some light coming in, bounces off the primary, up to the secondary, down onto the tertiary, and then into the camera, which is the size of a car, mounted upside down, hanging on top of this mirror. Here is the mirror when it was under construction in Arizona at the Mirror Lab at the University of Arizona, the Steward Observatory. And you can see here how it's been made. It's a parabolic mirror that was first cast, and then a spherical tertiary mirror was ground out of the middle. It took quite a while to grind all that glass out. In fact, it took 7 years to build this mirror. Here's me, at least younger me. This was me in 2008, after 1 year of mirror fabrication. It was finished in 2014. So I was already working on the project then, and still going now. That's how awesome it is. Okay, so where is M1, M3 now? Well, it's actually installed in that cleaning facility. It's being prepared for observations. It arrived last year, shipped on a container ship. Here's a fun photo. This is the primary mirror of the Simone telescope being taken through the tunnel at the Piclaro Dam on the way up to the summit at Cerro Pachon. And you can see it just fits through the tunnel by design. Here's a sense of scale for you. Here is the mountain, Cerro Pachon. Up there on the right, you can see that's the dome of the Rubin Observatory. Over here, you can see the Gemini South telescope, same mountain. And here you see M1, M3 in convoy being taken up the road on the way to the summit. Okay, so the Simone telescope has one instrument only, and its name is LSST-CAM. This is the biggest digital camera in the world I mentioned briefly. What does it mean to be the biggest camera in the world? Well, it has 3,200 megapixels. I forget where we're up to with our phones. Is it 10 megapixels now? So this is 3,200. Another number that's hard to visualize, so I'll spend some time trying to help us understand what it means to be that big. Where are we now? This is the focal plane with all the sensors, or the CCDs that collect the light, mounted and installed in the clean room at SLAC. This is where we're building the camera, just up the road. The sensors are all installed, and we're testing the refrigeration system. This camera has to work at low temperature. And pretty soon we'll have LSST-CAM's first image, so watch out for a press release about that. It's going to be fun. In the clean room at SLAC, you can see here the camera is pointing downwards. That's how it will be for most of its life, right? Because it's mounted above the tertiary mirror looking down with the night sky up there. Oh, and you remember I said it was the size of a car hung upside down over the mirror. You can get a sense of scale in this picture on the right-hand side. This is the clean room at SLAC where the camera's being assembled. That's part of the camera body. And by the time it's all been put together, all the various pieces, the back of the camera will almost touch the ceiling. I used to think that it must be something like a Mini or something like that when we said the camera was the size of a car. It's more like a sedan. Okay, so we're on schedule and due to start a 10-year survey in October of 2022. So that's the date to remember, survey start. There'll be first light before then, and we'll do some commissioning observations and so on, but the survey will start October 2022. Okay, so just like Magellan, we have a crew of hundreds of scientists, engineers, and support staff. Not so good in a storm in the South Atlantic, but great for putting together an observatory of this scale. So here's just a sense of the people who are currently building the Rubin Observatory. And here are people gathered together from universities all around the world who are planning to use the Rubin Observatory to do cosmology. And in the second half of this talk, I'll tell you a little bit about some of the science that we're planning with it. Okay, so the Rubin Observatory is designed the way it is in order to be a very fast survey telescope. That's its main characteristic. It has a big mirror to collect a lot of light. We go through those 3 reflections in order to make a very good image over a wide field of view. And so we can take big images and then cover the sky very quickly. We slew fast to go from one place to another very quickly. We're going to build up an image of the night sky every few nights. And then we'll do it again and again and again. So here's a picture on the right-hand side of the sky coverage, roughly. We haven't fully optimized this yet, but it will look something like this. What you see here is all of the southern sky covered with, as you can see on the color scale down here, something like 150 to 200 images over 10 years in each of 6 filters. So what does this mean? You can think of it as a Technicolor movie of the night sky taken over 10 years, where we go back every few nights and take another image at each patch of sky. And so if you imagine just focusing in on one galaxy, say, we'll be able to see how that galaxy varies over 10 years. All the things that could happen in that galaxy we can start to study. Very exciting. So an 825-frame movie in 6-filter Technicolor. And the name of this 10-year survey is the Legacy Survey of Space and Time. Okay, so I didn't mention this at the start. I thought I'd try and do this all with a straight face. You might know of the Rubin Observatory as the LSST, the Large Synoptic Survey Telescope. It was renamed earlier this year in honor of Vera C. Rubin. But we wanted to keep the acronym because we had so many things named LSST. So now the survey is LSST and the observatory is Rubin. We might consider, I think, doing a second survey after 10 years if we have enough scientific reasons to do that. That would have a different name. It wouldn't be LSST, it would be something else. Okay, so biggest camera in the world. What does it mean to have such a big camera? What does 3,200 megapixels mean? Well, here's a picture of the night sky over which I've laid a layout of the camera focal plane. So you can see for scale here, the full moon is in the top right-hand corner. So for professional astronomy standards, this is a huge field of view. It's not so big for us with our eyes that can take in all the night sky at once, or even for, if you have a telescope at home, you can easily get a big field of view, bigger than the LSSTs, the surveys. But for the images in the survey, what makes them special is not only are they wide field, they also have very small pixels, which means we can take high-resolution images. And in fact, if you wanted to print out one of the images from the survey at standard printer resolution, 72 dots per inch, you need a 70 by 70 foot piece of paper and 3 tennis courts to lay it out on. All right, so this is still somewhat head-hurty. Let's try zooming in to get a feel for what will be in one of these survey images from the LSST survey. So here's the full moon, a bit easier to imagine. Don't forget, though, the size of the full moon is the tip of your pinky at arm's length. That's how big the full moon is. Anyway, here we are, zoomed in on the full moon. Now let's take the moon out of the way, and here's what the night sky, the deep night sky, looks like behind the full moon. So you can see some nearby galaxies here. Here's one. Everything with a funny sort of hole in the middle where the detector is saturated, that's a bright star. This isn't an image from the Rubin Observatory, of course, we're not on the sky yet. This is an image from the Canada-France-Hawaii Telescope Legacy Survey. But it's not very different from what we expect to get from the Rubin Observatory. Okay, so let's zoom in a little bit more. This is a patch of sky the size of the full moon. Oh yeah, here we go. This is a hair held up at arm's length for orientation. Let's zoom on this little patch of sky down here. Happens to be very interesting. Here's the hair again. See how wide that is. And you can see right in the middle there is a very interesting object. This is a gravitational lens. So it's a group of 4 massive galaxies that happens to be sitting in front of a distant faint blue galaxy, and it's acting like a very badly designed lens. The light is coming both ways or several ways around this massive object and being refocused towards us. So we see multiple images of the background galaxy. So I put this up here because I like to study these. I think they're very interesting objects. They're very useful for cosmology, and I'll come back to that in a bit later. So that's what it means to have a wide field of view and small pixels. And this is why we're going to end up with hundreds of petabytes of data. Okay, so what will we do at the data facility at the Rubin Observatory? Well, we take in these images as they're taken. They'll be piped up to us over special internet cables from South America. And within a minute or so, we'll have reduced these images, compared them with a previous image or an earlier image of that same patch of the sky, and made automatic measurements of things that have changed. And then once a year, we'll go through all of the images and update our measurements of everything, including the things that haven't changed. So the key here is the automatic nature of the measurement. So we'll have computer programs going over these images, measuring the stars and the galaxies, measuring their brightness, their size, their color, all these things, and then putting them into a database. Here's a view of a database. And this database will be available to all astronomers in the US and many astronomers around the world to do science with. A good fraction of it will also be available to anybody to do science with, and I'll come back to that towards the end. Okay, so what about some of the science we can do with the images coming from the Rubin Observatory, these LSST images? Okay, so the survey will provide us a census of the solar system. We have 8 planets, check. But there's a whole bunch of other things that we can measure in the solar system. And the survey will contain information about 5 million main belt asteroids, 300,000 Trojans, they're the asteroids that are in Jupiter's orbit, 100,000 near-Earth objects, they're the ones that we might have to worry about, like the dinosaurs did, and 40,000 Kuiper belt objects, which I'll come back to in a second. So all of these are automatically detected as moving objects. In one frame of the movie, they're here. In the next frame, they're over here. So what can we do with these Kuiper belt objects? Well, turns out that if you look carefully at the orientations and the spins of the 8 planets in our solar system, there's some weirdnesses about them. They're not quite what you'd expect. Some of them are tipped on their side, some of them are rotating the wrong way. And it turns out to explain those odd motions of planets in the solar system, one way to do it is to have a 9th planet that used to live in the solar system and has been ejected at some point in the solar system's history. Where is it now? Well, it's predicted to be somewhere outside the solar system, but not very far outside the solar system, and in fact, in the Kuiper belt. So planet 9, we can take these models that explain the weirdnesses in the planets' orbits and orientations and make predictions for where planet 9 could be, roughly. But we can't make very precise predictions of where it is. We can just say roughly where it is. What you need is a big sky survey to go looking for something bright crossing the images. So this is something we can do with the LSST images. We can go looking for planet 9. We think it's out there. We'll go see. Let's go a bit further out into the galaxy. Here's an ocean of possibility. Once you start taking multiple images of the night sky every few nights, you start to build up a sense of how everything is varying in brightness over time. We call it their light curve. But you can imagine, there are stars that get brighter and fainter and brighter in some periodic way. There are stars and other things that explode in interesting ways that we can study. Here's a chart that captures all the explosions we currently know about, types of explosions. There's intrinsic brightness increasing that way, and the duration of the explosion increasing that way. So we know about novae, for example, nuclear explosions on the surfaces of stars. They're over here. They last about 3 months, and they're about that bright. If you go up the chart, you get up to supernovae, things that are even brighter. That's where the whole star blows up. And you can see over here, there's all this space where we just haven't looked. And we haven't looked because we haven't been able to take repeated images of enough sky to find them yet. So we'll get to go see with the LSST. So right at the start, I showed you this map that Ribeiro had made, Magellan's map maker. The main result, I called it, of Magellan's voyage. Well, we can also think about maps we can make with the LSST images. And it's good to remind ourselves that maps are, they're not data, they're not images themselves, they're sort of simplified representations of images. When you dial up Google Maps, it's fun to look at the image behind it, if you want to see your neighbor's house or something. But if you actually want to make predictions about how to get somewhere, you want to look at the map view. So we do the same thing in astronomy. We have all the images of the night sky, but actually the automatic measurements filtered in various ways allow us to build up simpler views of that data, maps of the universe at different distances or different scales, and we can learn a lot about what's there and where we should be looking for other things. So what does it mean inside our galaxy, mapping the Milky Way? Here's what happens, not for the Milky Way, but if you image two relatively nearby galaxies and you go from a shallow image to a deeper image, you start to see all these features in the starlight from those galaxies. Where do these come from? Well, we think these are trails of stars left behind after the two galaxies have merged into one, and then the third galaxy has merged in to make this galaxy even bigger. And every time you get a merger, you get a trail left behind. And so images like this allow you to do sort of fossil studies of the history of galaxies. How were they built up? And we can do the same with our own galaxy. We can look for streams of stars around our own galaxy. Here's an early study of this with a shallower survey, the Sloan Digital Sky Survey. With the LSST images, we'll be able to go deeper and find more streams, map out more of the history of our own galaxy, and start to understand a bit more about where did we come from, how was our galaxy made. So, it seems like a good place to pause for a second and say thank you to the inspirational scientist after whom the Rubin Observatory is named. So, here's Vera Rubin in 1975. Working on a very interesting question, which is how fast do the stars move in other galaxies like our own galaxy? And so she made very accurate measurements of the speeds of stars in galaxies, both near the center of the galaxy and then as you move further away from the center. And what she found was that the stars out here, a long way from the center of the galaxy, were still there and moving very fast. The still there is important. If you're moving very fast and you don't escape, that means there's something stopping you escaping. The only thing we know about that stops stars escaping from galaxies is gravity. And so if it's gravity holding these stars in, then what's doing that gravitating? If you add up all of the mass that you can see here in stars in the galaxy, it's not enough. It's not nearly enough to keep these high-speed stars from escaping. And so what Vera Rubin had found was the first evidence for dark matter in galaxies. A remarkable thing. So galaxies are heavier than they look. By mapping out the streams of stars in our Milky Way, the leftovers from mergers that made up our galaxy, we can start to ask, what is the dark matter made of? Well, how does this work? Once you've found a stream, you can look for disruptions to that stream. Imagine a stream of stars across the sky, and imagine sometime in our history, a dark clump of dark matter flew across that stream. You might expect to see a little kink in the stream. And in fact, that's what models predict. Here's a model up at the top. Maybe you can see that little kink in black along the way. If we find something like that, it will tell us something about what kind of matter dark matter is. Cold dark matter doesn't interact very much. It will have a different density profile for this clump of dark matter that's flown through the stream. If it's a different kind of dark matter, it might be a fuzzier cloud of dark matter that flew through the stream, and it wouldn't make such a pronounced kink. So by studying the detailed structure of these streams, we can hope to say something about what dark matter is and make Vera Rubin proud. Okay, Vera Rubin, I said she was an inspirational scientist. Here she is, running the show on an observatory floor. One of the very famous things she said, "There is no problem in science that can be solved by a man that cannot be solved by a woman." Next time in your life, if you happen to have the thought that maybe a man could do a job better than a woman, you should remember this photo. Here's Vera Rubin telling you that you're wrong. Okay, let's move further out, outside our own galaxy, out into the extragalactic sky. Okay, so moving outside our own galaxy, let's see what the LSST can do for us in extragalactic astronomy. Well, just like mapping out the stars in our own galaxy, we'll be able to map out the galaxies outside the Milky Way. And we'll be able to do that to great distances, looking further and further back in time. We'll map out the positions, brightnesses, colors, and shapes of several billion galaxies. What's this useful for? Well, you see here that we expect galaxies to be clustered into clusters of galaxies, but also clustered into filaments between clusters of galaxies. We expect to be able to see that. Why do they do that? Well, they're tracing out where the dark matter is, where the dark matter has flowed together under gravity in order to make something like this. So this is the underlying dark matter structure in this simulation. And I was showing you the galaxies in that simulation. How could we get at where the dark matter is directly? Well, it's very hard, it's dark. But what it does do, as Vera showed, it gravitates. So rather than looking at the speeds of stars under the gravity of dark matter, we can look at the deflection of light under the gravity of dark matter. So remember those gravitational lenses that I showed you a minute ago? All galaxies in the universe are acting as gravitational lenses. These filaments of dark matter are acting as gravitational lenses. Maybe not strong ones that cause multiple imaging, but weak lenses that cause little distortions in the positions and especially the shapes of background galaxies. So if we look for coherent distortions in the shapes of background galaxies caused by the filamentary structure of dark matter in the foreground, we can start to understand something about that filamentary structure. First, is it there? Second, how has it formed? Has it formed in the same way that our simulations would predict? And has it formed at the same rate that our simulations would predict? We can start to get at that by making these weak lensing maps. So here's a picture of what's going on. Light from a background blue galaxy flying through the universe past all these filamentary structure of dark matter. And as you can see, as the light ray travels from left to right, the universe is changing. It's getting clumpier as the dark matter falls together over time. And so we can try and make maps at different distances from us of the dark matter and watch this cosmic history of structure forming. Amazing thing. We've made some progress on this already. It's one of the ways that we've been studying the universe and its expansion history. And you probably all know this, but it's good to remind ourselves that there's something odd about the cosmic expansion, the expansion of the universe. We've known for a long time that the universe is expanding, that it started in some hot Big Bang, expanded very rapidly, and then started to slow down as the stars and galaxies formed over the course of billions of years. The unexpected thing was that sometime in the recent past, a few billion years ago, that expansion rate seemed to, instead of slow, speed up again. So the expansion of the universe is accelerating, and no one knows why. I put this picture up to try and illustrate just how weird this is. It's as if you threw a baseball in the air, and despite you knowing, or thought you knew, that under gravity what goes up must come down, the same is not true of the universe. So this is perhaps the biggest mystery in physical science, and we should do everything we can to try and understand it. One way to understand it is to come up with ideas for what could be going on. That's what the theorists do. What can observers do? We can try and make the most accurate measurements we can of the expansion in order to rule out some of the ideas, most of the ideas, hopefully all but one of the ideas that the theorists come up with. So that's our program. How do you measure acceleration in the universe, though? It's hard enough to measure distance. How do you measure acceleration? Well, if you think about this San Francisco street, how would you measure the acceleration? Well, if you remember high school physics or something, all that time you spent rolling trolleys down hills and timing things, do you remember that? The steeper the slope, the faster the trolley fell. You didn't even need to go to high school for this. You just roll balls down hills, and you know that the steeper the grade, the higher the acceleration. So if you want to understand acceleration, one way you can do it is to try and estimate the gradient that the ball is rolling down. You could look at the ball directly. You could study the dynamics of falling objects. And we do that with, for example, stars in galaxies, the dynamics of falling objects, orbiting objects. We can also do it by galaxies falling together under gravity. That tells us something about the acceleration going on. But we can also do something else. We can try and estimate this gradient directly. What does it mean, gradient in the universe? We can try and estimate the relationship between distance and apparent speed. How would you do it in San Francisco? Well, if you knew that all these cars' headlights were the same brightness, you could estimate how far away they were, and then you can look at how high up the hill they seem to be, and you could make some estimate for how steep the hill was. Hopefully that's plausible. The corresponding thing in observational cosmology is to use certain objects as standard candles, where we think we know what luminosity they are, what intrinsic brightness they have, and then use those to measure distance and compare with their apparent speed going away from us, their redshift. All right, so standard candles, LSST, the survey, will contain hundreds of thousands of supernovae that we can use to do this. Type 1a supernovae, it turns out, all look roughly the same. They're standard candles, or at least standardizable candles. We can use them to measure distance. If you have several thousand new supernovae detected every night, you start to build up a big enough number that you can ask questions like, is the acceleration the same in that direction as that direction? Is the universe expanding in the same way over there as it is over there? I like to point down because I have to remember that the survey is being taken in the south. Okay, so how well do we think we can do? Combining all the different ways we have of measuring cosmic acceleration with the LSST survey data, we think we can get to 2% precision, and also do cross-checks to make sure we haven't made any mistakes. So that's a big program, 10-year program, and you should get people to come in here and give you updates every now and then. Okay, so I wanted to spend just a few minutes telling you our little piece of this program at SLAC. Actually, we have several pieces, but let me be honest, my little piece with the people that I work with directly. So we use these strong gravitational lenses to measure distance in the universe. Each one, it turns out, can be a very accurate measurement of distance. And it's because when you have this multiple imaging effect, you see multiple images of the same background object. If that object is varying in time, flickering, then you can imagine that you see the flickerings at different times in this image compared to this image, just because the light is traveling on different paths. And so there's a delay between the images. We can measure that time delay, and it turns out we can use that to measure distance. Now, LSST will provide measured time delays for hundreds of lens systems and information about these massive galaxies that are doing the lensing for thousands more. So here's a preview, if you like, of the kinds of lenses we expect to be able to find in the LSST survey images. Now, it turns out you not only have to measure the time delay between these flickerings, you also need a very good model for the mass that's doing the deflection. You have to understand where the mass is, where the dark matter is in this galaxy, in order to be able to use it to measure distance. And it turns out to do accurate cosmology using these lenses, you have to spend a lot of time modeling each lens. At the moment, it takes us several weeks, computers running full speed, to do the modeling analysis. So we started to ask ourselves, well, how can we scale this up to LSST? The size of the LSST dataset makes us think differently. And this is going to be true for many astronomers, I think. We have to think differently about the way we do our analysis. So since we're in Silicon Valley, we've been trying to learn from our colleagues down the road, and we're using artificial intelligence to do super fast lens modeling. You're probably aware by now that the tech companies in Silicon Valley have been using neural networks, deep learning networks, to do facial recognition. You make a neural network and you show it millions of images of faces, and gradually the network learns what faces are, such that when it's shown a new photo, it can tell you who it is. So that's a classification problem that they are solving, basically solved now. So we're doing the same thing, except that we're not interested in the classification problem, this type of lens versus that type of lens. What we want to know is, what are the model parameters of each lens, so that we can make predictions with that model of what the time delay should be in a given cosmology. So we make millions of synthetic lenses where we know the true parameters, and we train the network to be able to just look at a new image and tell you what the model is. It's really cool. So how is this going? Ji-Won Park and Sebastian Wagner-Carena, they're the grad students at Stanford working on this, along with Simon Bira and Aaron Rubin and me. So far, so good. We're starting fairly simple. We have moderately idealized conditions, but we're finding we can do accurate cosmology with competitive precision about 10,000 times faster than current methods. So this is going to allow us to do new things that we hadn't thought of before, now that we can do things super fast. That's just a little taste of what we're doing at SLAC. Okay, so the Rubin Observatory will provide many different maps for others to follow. It's making us think differently. It's giving us new views of the solar system, of the Milky Way, of the extragalactic universe. Those maps for others to follow, those others could include you. How is this going to work? Well, one of the things we'll be doing with the Rubin Observatory is making it possible for anyone to take part in the science. So we have a system where professional astronomers can design citizen science projects for anyone to help out with. So for example, I work on one project called Space Warps. This is to find new gravitational lenses in deep sky images. It's been pretty successful so far. The volunteers who spend their time looking at images saying lens or not, they turn out to find different kinds of lenses than the machines do, which is pretty cool. So there'll be more projects like this with the Rubin Observatory data. We teamed up with the Zooniverse to make a system where anybody, in fact, can make a project. And so one fun thing is, are we going to see citizen-led citizen science projects? I think that would be great. But it makes us think, what does it take to be a scientist? You might be sitting in the audience thinking, well, I could never do that. But what does it take really to be a scientist? So let's ask Vera. So here she is as an undergraduate at Vassar College in the 1940s. But in one of her memoirs, she writes that her childhood bedroom had a window that faced north. And at about age 10, she started watching the stars go across the sky. And by age 12, she'd prefer to stay up and watch the stars than go to sleep. And she started learning, inspired by this, going to the library and reading. There was just nothing as interesting in my life as watching the stars every night. That's how inspirational she found the night sky. Some of you might recognize that feeling. She found it a remarkable thing, she says. You could tell time by the stars. Throughout the night, I would memorize where each meteor went so that in the morning I could make a map of their trails. Even then, she says, I was more interested in the question than in the answer. I decided at an early age that we inhabit a very curious world. So what does it take to be a scientist? I think two things. First thing is you have to be curious. You have to want to know how the universe works. And the second thing is you need to never, ever give up. Okay, so what will we do for helping budding scientists, young and old, get to know the LSST data, start thinking about how to do science with the LSST data, how to do astronomy as citizens? Well, here are some tools that will go out into classrooms to introduce students to the data, introduce concepts to do with astronomy. There's an awful lot of teaching we can do with the LSST data. We'll have a sky viewer that allows you to browse around the night sky and learn about galaxies and stars and go and see what's happened to your favorite objects lately. Try and understand these light curves and maybe make some contributions. But certainly give everyone a sense of the adventure that we're on. Okay, so here's Vera Rubin again. She gets the last word. So she says, the joy and fun of understanding the universe we bequeath to our grandchildren and to their grandchildren. That's what we're going to give them. And with over 90% of the matter in the universe still to play with, even the sky will not be the limit. Okay, thanks very much for listening.
So you were talking about megapixels, gigapixels resolution, and the technical parameters, but the atmosphere gives us certain distortion. So I would like to ask, what's the like a balance trade-off between going the pixels size, like the resolution-wise, versus the distortion? So what's the limit we can go taking into account the atmosphere and for all those 6 color filters?
Yeah, great, thank you. So it's true, I said we have a lot of pixels which allows us to make high resolution images, but really the way we should think of it is the atmosphere, as you say, sets a limit to what resolution we can get. We go to high mountains in Chile, which are very dry, very high. They give us very good image quality. That really limits the resolution. So the median seeing, as we say, is 0.7 arc seconds at Cerro Pachón. What that means is that there'll be each star in a typical image will appear as a round blob, roughly 3 and a bit pixels across. And in fact, we knew what the image quality at the site would be when designing the camera and the optics. And we chose the pixel scale to be such that every star in a typical image would be 3 and a bit pixels across. So the design of the telescope matches the quality of the imaging at the site. Now, a typical image will be that resolution. But sometimes not so much the weather, but the conditions in the atmosphere, maybe it's a bit windy at high altitude or something, will be such that the images will be blurrier than that, and the images won't be as good as 0.7 arc seconds. On the other hand, sometimes you'll get a very still night, and you'll get an image that is better quality than 0.7 arc seconds. So one way to think about the LSST survey data set is that you're sampling the distribution of resolutions. And if you wanted to make the best possible image, you could just take the images that had very high resolution, where the atmosphere was still, and make an even higher resolution image. But roughly speaking, that's what the trade-off is. We chose designed the optics and the camera such that stars would appear to be typically 3 and a bit pixels across. There's a bit of variation from one filter to the other. The Z band tends to be better quality than the bluer bands, but roughly speaking, the 3 pixels across in the I band gives us a pretty good range of resolutions.
So 2 quick questions. One is, what visual magnitude can you achieve in your typical image?
So in a single visit, we get down to about 24th magnitude. Did you hear the wow over here?
Yeah, that's pretty
Did
decent.
you pick that up on the recording? Thank you.
The second question is, you show the field of view in that picture. What would the Hubble field of view be compared to that? I imagine it's pretty tiny.
It is pretty tiny. I used to... let me see if I can remember. So the Hubble field of view is several arc minutes across, and the full moon is 30 arc minutes across. So if you think of the eye in the man on the moon, that's about the survey camera on HST, roughly. I might be a little bit off, but roughly speaking.
Okay. Thank you.
Thanks. You're welcome.
Hello, thanks for the talk. How would you describe the light sensitivity of the sensor array?
How would I describe the light sensitivity of the array? It's incredibly good, but I mean, these are very advanced sensors, but they're not sort of super special. And I'm qualifying this a bit because I know that there are sensors out there that are better behaved in some respects than others. What we're doing is we're using new sensors that are very thick, have very deep wells, can do the imaging very reliably, but there are better sensors in other cameras. What's different about the LSST cam is the scale of it. So we have very good sensors, we have a lot of them, and we need to keep all of them going for a long time, so it has to be reliable. So I would say we have better than average light sensitivity, but we're going for scale and reliability.
Thank you.
Oh, sorry.
My turn, right, sorry. My question is, if we could see anything beyond the Andromeda galaxy, what would it be?
Sorry, could you repeat? If we could see anything better than?
If we could see anything beyond the Andromeda galaxy, what would it be?
If we could see anything beyond the Andromeda galaxy. So the Andromeda galaxy, for the rest of the people in the room, that's our twin galaxy, right? That's how we should think of it. Andromeda is our nearest big neighbor. It's coming towards us and so on. It's a member of the local group. It turns out we can see many galaxies beyond the local group. There's a local cluster, and then beyond that, as I was saying, there's billions of galaxies out there in other groups and clusters further out. And it's interesting to then compare the galaxies in our local group with other groups that are like ours and start to understand a bit more about how special our galaxy is. So far, it seems like it's not a very special galaxy, but maybe we'll learn more by making more and more comparisons with more and more galaxies as we look further and further out.
Thank you.
You're welcome. Thanks for the question.
Hi, I have a question about out beyond the Andromeda galaxy. So since you'll be able to look at the large-scale structure of the universe, and it's a space and time survey and goes back in time as you go further in space, and you're going to be working with theoretical models, my question is, once you've sort of used the actual data set to home in on some nicer theoretical models of the large-scale structure of the universe and its formation, will you then be able to extrapolate what the universe looked like at different times if you didn't have to worry about the speed of light? In other words, if you had like a God's eye view and we're taking a snapshot where time wasn't a factor, but like this is what the whole universe, visible universe, looked like at 5 billion years and 10 billion years and 13.7. Will you be able to do something like that with any accuracy?
Yes, I think we will.
Cool.
So in the patch of sky that we're looking at, and remember that's half the sky, so it's a big patch. In that patch, we'll be able to make 3D models of the large-scale structure at different distances from us, and as you say, hence at different times. But of course, we'll still only be able, when we're doing that, we have to think time and space at the same time. Here's the bit of the universe that we'll see as it was a few billion years ago. And then here's the bit of the universe that we'll see as it was 10 billion years ago. And then we can maybe make another one a bit further out than that. And so that's showing us a patch like this in a sort of shell around us. So that's a lot of information about what the universe was doing at that time and how the universe behaves in general. But if you think about it, it's still a fairly small fraction of the universe. I think what's going to be interesting is to take that information in that shell and use it to constrain a model of the entire universe, where we have the CMB, the microwave background that constrains what it was like in the very early universe in a shell very far out and all the way around. And then we'll have more information in half the sky in these other shells. And I think we want to make a model that explains all of those data and starts to show us what the 3D structure of the universe was like at any time. And I agree, I think that was a super cool project, and we made a small start on it. We started with the CMB data, and we just looked at the largest scale fluctuations, like roughly how much mass is over here compared to roughly how much mass is over here. And then we started to try and play that model forward in time to say, well, what would that mass be doing 10 billion years later? And so we're very low resolution at the moment. What we'll get from the LSST data is a much sharper view. Everything will kind of come into better, crisper resolution. And it will be enormous fun to make that movie and play it for ourselves.
Thank you.
Your graph of the duration of the brightness versus the magnitude of the brightness leads me to ask the question, if you got a resolution of only a few days, is that going to be useful for doing something like searching for optical SETI signals?
Let's see. So it's true, we'll come back on average every few nights. But it turns out we won't be very strict about that. Actually, we'll come back to any given patch of sky. We'll take a 30-second, effectively a 30-second exposure. It might be a pair of 15-second exposures, but anyway, a single visit. Turns out we'll come back to that patch of sky 30 minutes later. And the reason for that is to try and track the fast-moving objects. 30 minutes is about what you need to see something move within our field of view and be able to link them together. So we'll do it every 30 minutes. We may then come back the same night a few hours later. And then a few days later, we'll come back and do the same thing. But it won't always be strictly 3 days. Sometimes it'll be 2 days, sometimes it'll be 5 days, occasionally it'll be 1 day. And so we'll start to build up irregular sampling in time. And that's what will allow us to search for faster variations. Now, your specific application, how much will it help with the search for extraterrestrial intelligence? I have to admit, I don't know. I've been puzzling more about explosions of stars and things like that, where I think there is a lot of unexplained and as yet undiscovered explosions likely to be out there for us to study. But it could be that we learn something interesting about SETI as well.
Thank you.
Oh no, now I'm on camera saying that it could be interesting.
So just some information that may be of interest. Your mirror was done at the Mirror Lab at the University of Arizona in Tucson. They offer public tours several days a week. And I've taken the tour, and it's absolutely fascinating. Anyone who's in the Tucson area, highly recommended.
Thank you, that's a great comment. In fact, just as another teaser for people who are thinking about going on holiday to Tucson and taking a tour around the lab, what was most fun for me was how they make these parabolic mirrors. Turns out if you have a bowl of liquid and you spin it, the surface of the liquid, just under gravity and in centrifugal force, makes a parabola. And they do that with the molten glass. So they have these big vats that are turning and maintaining a nice parabola as the glass very slowly cools and sets. It's so cool. I agree. Definitely worth a visit. Hi.
Thank you. I did a back-of-the-envelope calculation, and I think you're going to be pulling down about 50 terabytes a day.
I think that's right, yeah.
Can you discuss your storage format?
Do you remember those floppy disks in the 80s?
You're not using those.
Not that. Okay, so...
And not a DOS text format either.
So like I said, the images will stream over special internet up to the data facility in the States for processing, and we'll keep those images stored on disk while the processing is happening. Eventually, I forget what the plan is. After 1 or 2 data releases, we'll start to archive on tape, which is still the best sort of high-density format for long-term storage. But in the meantime, we'll keep things on disk. And
as separate images in a directory?
As separate images in a directory. I suspect not, because I think we'll hit the limits on the number of files you can fit in a directory. So I think there'll be we'll use a file format that allows multiple images to be stuck together.
Thank you.
Hi.
So, thanks again. There's somebody who lives nearby here who's putting an awful lot of communication satellites up in orbit. How is this project of his going to affect what you're going to be doing?
Okay, so for those of you who haven't been following, the question is about these low Earth orbit satellites that companies like SpaceX and others are putting up. What their goal is to provide internet to people all around the world who may not have coverage. So it's a very worthy cause. But these low Earth orbit satellites look very bright. Maybe you've seen them launched in constellations of, you see them as streams of satellites going across the sky. Very bright. You see them at dusk and dawn because they're in low Earth orbit. So it's kind of like the space station. You only see them at dusk and dawn. But the question is, what impact will that have on the legacy survey of space and time? So the short answer is we don't know yet, but we're working on it with SpaceX. So the chief scientist for the Rubin construction project is working closely with them. In fact, the last launch that SpaceX did, one of the satellites had been darkened. They painted some of the surfaces to try and reduce the brightness. And we're taking observations of those satellites in that particular little constellation. We'll have more results on that later this spring. So you can see where we're going with this. We're trying to understand first how bright they are and what we can do to make them less bright. And then on our side, we can ask questions like, how could we take the observations? How can we process the data in such a way to mitigate the effects? Basically, what you'd see in an LSST image is a very bright streak across the image. We think that in our current planned exposure time, it wouldn't saturate the image, but it would be very bright. And so we would have to do something to try and get rid of that band, or at least cope with it. So we started thinking about things we can do with the data. But it's a good question. I was thinking about this in the car on the way up here because I thought you might might ask this. And I remembered another story from Vera Rubin actually about similar things. When she started work at an observatory, I forget which one it was, sorry. She started work at an observatory. She was the only female astronomer there. And her new male colleagues said to her, well, you're going to have some problems using the facilities. We never had a woman astronomer before. We only have men's rooms. And so what she did was went back to her office and cut out a triangle of paper and went back to the door of one of the men's rooms and just stuck it on the picture of the man, and then said to her colleagues, look, now you have a ladies' room. So this is why I think, to be a scientist, you never ever give up. Things like this come up all the time. There are new problems to solve, and we'll try and solve them.
Thank you.
Two quick questions. What % of the sky are you doing the survey on? Because it's only the southern hemisphere, not all of it. And the second one is, why SLAC? I mean, I don't see them as the forefront in astronomy.
So first part, it's about 50%. Not exactly 50% because we haven't fully optimized the survey strategy yet. It might be better to edge a little bit into the northern sky and cover more sky. But if you do that, of course, you can't go as deep in the southern sky. So there's a trade-off to understand. And we're taking input from all over the astronomy community as to how we should optimize the survey. The second part of your question, why SLAC? So it's interesting. A few years ago, the Department of Energy that provides funding to SLAC to do its research, they followed the high energy physics community's own survey of the physicists and what they wanted to do over the next few decades. It's called the SNOMAS process. It's something we go through every few years. And it turned out that particle physicists, the high energy physicists, were interested in cosmology. You can do fundamental physics by studying the night sky. This property of the universe, that it's expanding, points towards there being a new force or a new energy field that's causing this acceleration. And that's of great interest to high energy physicists, including those at SLAC. In fact, we have high energy physicists who previously worked on the Babar experiment, doing particle physics, who've moved into cosmology. In fact, Aaron Rubin is one of them. I showed his name. He's working with me on the AI for lens modeling. So we should think of cosmology as part of high energy physics. It's getting at the fundamental physics of the universe in a way that particle physicists are interested in, and that's why SLAC is interested in doing this.
And perhaps another question, what's the budget?
The budget for this project?
Correct.
So it's to build the Rubin Observatory is between $400 and $500 million. to operate it is going to be between $700 and $800 million. Could be less over time. The way you should think about the cost of the Rubin Observatory is a $1 billion project. Another way to think about billion-dollar projects, or other billion-dollar projects you could have in mind, are a new runway at a major airport. That's a $1 billion project.
Or one election for one individual.
Yes, exactly. Exactly. Two more questions. Okay, one from this side, one from this side. Okay, good.
So how are you going to be affected by, correct for, take advantage of the displacement from the Earth's orbit?
The displacement from the Earth's orbit? How do you mean?
The Earth is moving in the circle.
Okay. So, sorry, I've got jargon on the brain. I know that as parallax. So we can use the fact that the Earth is moving around the sun from one side of the orbit to the other every 6 months. We can use that to get a handle on how far away nearby stars are, so-called parallax distances. We'll be able to measure parallax distances to many more stars than we have been before because we're able to look so faint in any given image. And so this is part of mapping the Milky Way. It will give us allow us to go beyond what the Gaia satellite has done, extend that model out to greater distances, and get a much more precise picture of the Milky Way and all its stars, and allow us to do better at this sort of fossil record of how the Milky Way was formed. But yeah, it's true. We should be able to do extremely well at parallax distances and go beyond the Gaia satellite.
Well, since it's the last one, thank you for a great talk. I was curious, you talked about making 3D models of of billions of galaxies, is what you said. This is an optical telescope, right? So it's not spectrographic. You can't measure redshift, even though you have 6, as I understand it, but please tell me. So how would you, if there's no variable in some galaxy that you see out there, how could you determine its distance?
Good. So I think I would quibble with we can't measure redshift. I think we will be able to measure redshift.
Okay.
As long as you kind of go with me a bit on what it means to measure something. So to measure the redshift of a galaxy, normally you'd take a spectrum and you'd see all the emission lines and absorption lines and you'd match up the emission lines with where they're supposed to be and you'd get a very accurate redshift and you'd say, haha, I know how far away that is once I've assumed how the universe is expanding. So forget about all that cosmology stuff for now. Let's assume we know how the universe is expanding. We can measure redshift and estimate distance and then start to build up 3D models of the universe, as you say. So we don't have a spectrograph. We can't map out a spectrum in very fine wavelength bins that allow us to see emission lines and all the features. But you can think of 6 filters as giving you a very low resolution spectrum. You have a brightness point here, and one here, and one here, and one here, and one here. And that shape of the galaxy spectrum, you can infer the redshift from that low resolution spectrum made up of the 6 wavebands. Now it's only a question, how accurate can we do? How accurate can we be at measuring redshift? That depends on what kind of galaxy it is a little bit. But we think we should be able to get photometric redshifts, that's what we call this, photometric redshifts to 5% for the easy galaxies, maybe 10% for the hard ones, and occasionally there'll be catastrophic errors where we completely get it wrong, but there are ways to get around that by looking at the neighbors of these galaxies. You expect galaxies to cluster together, and so you'd be surprised to see a very nearby one in amongst a lot of distant ones. So I think we will be able to do pretty well with photometric redshifts, well enough to support our big statistical understanding of things like explosions and variability in the universe. So I think we can measure redshift. We just have to cope with that uncertainty.
All right, thank you.
Let's thank Dr. Mark.